Look at any massive commercial vessel today, and you will see an enclosed, bright orange lifeboat. This is a highly engineered sanctuary, built to keep a crew completely isolated from the most hostile ocean conditions imaginable. This chart shows data compiled by the UK's Marine Accident Investigation Branch between 1989 and 2001. During that 12-year window, lifeboats caused 12 fatalities and 87 injuries. In that exact same dataset, the number of successful emergency evacuations was 0. While successful evacuations do occur globally, these numbers highlight an unsettling reality. The very equipment designed to be a sailor's last hope regularly becomes a deadly trap during routine, fair-weather training drills. When faced with mechanical danger, the maritime industry's instinct has been to add layers of redundant fail-safes to the original mechanism. But instead of guaranteeing safety, this compounding complexity creates hidden points of failure that can send a multi-ton vessel plummeting into the sea. In the early 20th century, sailors launched open wooden lifeboats by lowering them down the hull with thick ropes. Once the boat hit the water, buoyancy took the weight off the lines, allowing the crew to manually unhook the cables. But in a heavy ocean swell, the boat would violently jerk up and down. Sailors frequently lost fingers trying to wrestle heavy steel hooks free while under extreme dynamic tension. The limitation of that manual system became painfully obvious in 1980. The Alexander Keeland offshore accommodation rig collapsed. There were more than enough lifeboats available, but victims drowned because the boats never floated high enough to remove the massive weight from the cables, leaving the crew totally unable to release the hooks. To prevent this from ever happening again, regulators mandated an entirely different type of mechanism, an onload release system. The core requirement was that operators must be able to detach the vessel, even if the full weight of the boat is hanging in the air. The downward force of a fully loaded boat, holding up to 150 people, is geared down by a long tail acting as a massive lever. This translates into a tiny point force held by a semicircular cam. By pulling a remote cable, the cam rotates, the hook immediately opens, and the boat detaches. It is an effective piece of engineering. However, it introduces a terrifying operational hazard. By making it physically possible to release a boat under tension, you create the possibility of accidentally dropping a fully loaded vessel from 20 meters high in the air. To counter the risk of a freefall, engineers layered safeguards directly onto the onload mechanism. They inserted physical manual pins to force a deliberate two-step release, and they added hydrostatic interlocks, flexible membranes under the hull that theoretically only permit the hooks to open if the boat is resting in the water. But these secondary systems bring their own risks. Heavy steel fall prevention devices physically bypass the onload mechanism entirely, ensuring the hook stays closed. Yet these must be manually removed to launch the boat. In a high-stress scenario, a crew abandoning a sinking ship is forced to execute an intricate sequence of removing pins just to get away. The hydrostatic interlocks also routinely succumb to the harsh ocean environment. Debris and salt often clog the membranes after a drill, seizing them in the unlocked position and neutralizing the safeguard completely before the boat is even hoisted back up. In 1992, on the Ocean Duke, the cam inside the release mechanism failed to completely reset. Because it was resting at a slight angle, the geometric reaction point between the hook and the cam shifted. This exerted an immense, unintended force against the internal Morse cable until the line physically failed. The boat plunged, resulting in 6 fatalities. Layering secondary interlocks onto a mechanism that is inherently designed to violently release under load does not eliminate the core danger. It simply creates a highly sensitive network where minor rust or slight geometric misalignment can initiate a catastrophic failure. We can observe exactly how these mechanical cascades occur by looking at a modern incident. In March 2021, the state-of-the-art polar research vessel RRS Sir David Attenborough lay at anchor off the coast of Scotland. The crew took advantage of the calm weather to run routine familiarization drills with their lifeboats. After a few manual drops, they proceeded to test the dead ship launch. This specific procedure simulates a total loss of power on the mothership, forcing the crew to rely entirely on stored hydraulic energy to get the boat into the water. An operator pulls a remote wire through a roof gland.
This triggers a directional control valve, sending hydraulic fluid to swing the davits outward. To prevent the boat lowering early, a hydraulic interlock pin acts as the primary failsafe, sliding firmly into place to hold back a massive gravity brake. Only when the davits reach full extension does the pin pull back, allowing the remote wire to finally lift the brake and lower the boat. The entire sequence requires a precise mechanical choreography. The safety of a multi-ton launch rests almost entirely on one internal hydraulic pin engaging exactly when it is supposed to. During the handover period for the brand new ship, the owners temporarily suspended the planned maintenance system to handle the massive workload. For 16 months, that hydraulic interlock pin sat uninspected, its internal springs degraded and ultimately seized. When the crew member inside the boat pulled the remote wire, the seized interlock failed to hold its position. Without that blocking pin, the heavy gravity brake released at the exact moment the davits began swinging out. The lifeboat immediately dropped down to the deck and rolled violently onto its side. In a situation like this, the standard abort protocol is simple. Just let go of the remote wire to engage the brake. But the trapped crew member just couldn't. 2 years prior, shipyard workers outfitting the vessel had lost the original clip for that specific wire. They substituted a slightly larger clip. When it proved too big to fit through the roof gland of the lifeboat, they drilled the hole wider to make it work. As the boat rolled, the sharp angle of the capsizing vessel shifted the geometry of the wire. That oversized modified clip caught on the drilled rim and jammed immovably in place. The launch mechanism was physically locked open. With the wire stuck, the davit arms continued to mechanically extend, dragging the capsized boat over the edge of the ship. The forward fall wire completely detached from its hook under the extreme stress, sending the vessel plunging nose first into the ocean. A rusted internal spring and a slightly modified metal clip completely bypassed a multi-million-dollar redundant safety architecture. Fortunately, the crew survived without serious injury, but investigators discovered that this failure chain actually began with the manufacturer's installation. The ship was missing a dedicated deck launching station. Without it, the crew had no way to practice the dead ship drill using training wires, forcing them to sit inside a suspended boat just to test the equipment. The free fall was the result of discrete, seemingly uncoupled errors, an installation oversight, 16 months of suspended maintenance, and a minor field modification made to a small metal clip. When mapped against the overarching mechanism, we see how complexity obscures systemic vulnerability. A highly complex system makes it incredibly difficult for an operator to recognize when a sequence of tiny deviations has aligned to bypass every redundant node. The maritime industry spent decades attempting to engineer the danger out of the onload release hook, yet adding layers of pins, heavy strops, and hydrostatic interlocks has not altered the inherently dangerous physics of releasing a massive load under tension. It has merely multiplied the points where the system can fail. Reliability in extreme environments cannot be achieved solely through intricate mechanical workarounds. It requires rigorous operational maintenance and exact procedural compliance. Because if you continuously layer failsafes onto an unforgiving mechanism, the failsafe itself eventually becomes the fatal hazard.